In this video, we're going to define ionization energy of an element, and first ionization energy and successive ionization energies of an element, and we're going to look at what that process looks like from an equation standpoint and give you a couple of examples of kinds of questions we might ask about ionization energy. In a subsequent video, we'll look at the periodic trend for ionization energy. So ionization energy is defined, the first ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So it's this process. The element M in the gaseous state becomes a M+1 ion in the gaseous state, and in the process it's lost an electron. The energy change is the first ionization energy, I1. That value will be more if the element M holds on to its electrons more tightly than if it holds on to them not so much. So an important point to note, however, is that this process, I1, is always positive, no matter what the element is. Many misconceptions are students think that the alkali metals, which only have 1 valence electron, lose its electron so easily that it doesn't actually require any energy at all, and that's incorrect. All elements require energy to remove any of the electrons from them. They are being held, however weakly, by the nucleus, and it does require energy to remove them. So first ionization energy is always positive. The second ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous ions, +1 ions. So it is M+1 gas forms M2+ gas plus an electron, and that energy change is I2. Note, it's like taking the second electron off of the element M. The third, fourth, fifth ionization energy would all sort of follow suit. Important points to note. Ionization energy is always endothermic, so they're always positive values. So the energy should be always reported as a positive value because it always costs energy to remove an electron. Each subsequent electron is more difficult to remove than the previous one. The reason is that once you remove an electron, the remaining electrons are more tightly held by the nucleus. The positive ion is smaller than the neutral atom because the remaining electrons get pulled in a little closer to the nucleus, and consequently each subsequent electron that you take off is more difficult to remove. Again, common misconception is that that a group 2 will have a lower second ionization energy because it will result in having an octet, and that's not true. Even a group 2 element will have a more positive second ionization energy than first because the remaining electrons will be more tightly held. Point 3, the ionization energy is particularly large when removing an electron from an atom or ion that is isoelectronic with a noble gas, or that has an octet. So you will see large jumps in ionization energies when you are removing an electron from an atom or an ion that has an octet. So what kind of questions might you be asked? Let's look at this question first, and I will put the shade up so that you can only see one question at a time. Don't get distracted. Write the equation for the second ionization energy of aluminum. Okay, that means aluminum has already become a +1. It's had 1 electron removed. So the second ionization energy would be Al gas, Al plus gas. See, because it's already lost 1 electron. So the second ionization energy would be Al plus gas to Al2 plus gas plus an electron. And the change in energy is equal to I2, whatever that value is. It's experimentally determined. Okay, a little bit more complicated might be the following are successive ionization energies for an element. Which of the following elements could it be? Sodium, magnesium, aluminum, silicon, or phosphorus? Okay, well, let's look at these ionization energies. So one thing to note is each subsequent ionization energy is always greater than the previous. It takes 736 kilojoules to remove one mole of electrons from 1 mole of this element, and then it takes 1,445 for the next, and then it takes 7,330. Okay, so what we're noticing, if you look at this, at these successive ionization energies, here's a small jump, about 700 kilojoules jump in energy. Here's a large jump, okay, almost 6,000 kilojoules of energy is required to remove the third electron. So the first electron comes off relatively easily. The second electron comes off, okay, more difficult because it's more tightly held and it's smaller, but it comes off, you know, harder, but not excessively hard. But the third electron requires a massive jump in energy. Well, let's look at the rest of the pattern. This one goes up about 3,000. So it takes a 3,000. Remember, each subsequent electron is going to be more difficult than the previous. And then this one, another jump in 3,000. So you see this massive jump for I3, which means the third electron is likely to have been removed from an ion that has an octet, or that has a noble gas electron configuration. So which of the following would it be? Common misconception is to say I3 and you pick aluminum and then you got the question wrong. No. Make sure that you understand electron configuration. So the answer is Mg. And why? Well, Mg is 1s2, 2s2, 2p6, 3s2. So the first ionization energy removes the first electron from magnesium, resulting in the magnesium plus 1 ion, which is 1s2, 2s2, 2p6, 3s1. The second electron removed from magnesium results in Mg2+, which is 1s2, 2s2, 2p6, 3s0. There's no electron there. So this was easy. This was going from here to here, relatively easy. It's harder because it's smaller. Magnesium plus 1 is smaller than magnesium. So to go from magnesium plus 1 to plus 2 is difficult. But that third ionization energy, you're going from magnesium plus 2 to Mg3 plus an electron gas. Okay, so that's massive. That's going to be that 7,330 kilojoules to go from 2 to 3, because now you're taking an electron away from n equals 2, which is closer to the nucleus than n equals 3. See, the 2s and 2p is n equals 2, and it's an octet. This is not easy. Okay, that's why there's a big jump. Hopefully, this helps you understand the successive ionization energies and the kinds of questions that you might be asked about them.